Right, in 5.1, we've talked about estimating area using rectangles. And what we've done is we took a function and we put some rectangles underneath it using, in this case, midpoint, or in other cases we've used left or right, and we've calculated the area. And we used this y times this delta x, this space between, to get our area for each rectangle, and we added them all up. Well, we can do a similar thing with a sphere. If you take the curve y equals the square root of 4 minus x squared, and you spin it around this axis, you're going to end up with a sphere. And what you can do for a sphere is you can take your sphere and cut these little slices out of it. Let's see if I can draw this well enough here. And you have these tiny little slices that will tell you, they're like little cylinders, that will be able to tell you the volume of the sphere. So you have to imagine this sphere is, we've spun it around here, and we've got a big ball, a sphere, and we cut these slices, individual slices. Think about taking a basketball or a Nerf ball, one that's solid, and slice it into little bitty thin slices, and you get these little cylinders that will approximate it. There's a really good picture of this in your book in section 5.1. So we know that the volume of a sphere is pi r squared h. But let's look at this particular sphere. What's the radius of the sphere? Well, if we're using a midpoint, if we're using it onto the circle, then our radius of our sphere is just the function value, because that's where it's hitting. And the height of this sphere is this little amount here, our delta x that we're using. So if we put these in, we have the volume is pi times 4 minus x squared times our delta x. And we know that x has to be between -2 and 2. We can see that on our domain of our function, and we know that because that's what's going to be restricted because of the square root here. So what we can do is we can add up all these different volumes and end up with the volume of the sphere. So if we add up from -2 to 2 all the little slices that we make with using this formula, then we will be able to get the volume of a sphere. Now, if we're just doing, big cylinders and our delta x is just 1, then, it's not that big of a deal by hand. But once again, it's kind of tedious if we're going to do little cylinders. And remember, the more little cylinders, just like the more little rectangles we have, then the easier it's going to be to get a good approximation. So let's look at how we can use our program on our calculator to do this. Let's see if I can get it to... Okay, so you have to go back to y equals. Okay, and put in 4 minus x squared for your function, because the program uses y1 as its function. So if we want to figure out the volume of the sphere, we can use this circle function and its volume formula, because remember, before we just used the y equals, and then the delta x was taken care of as part of the program, depending on, because it split it into its delta, figured out what delta x was based on what our a and b were, our range from one to the other. Like here would be a, and here would be b, and then how many rectangles, or in this case cylinders, we want. So the program is going to find our delta x for us. So we just need the function that we want, which in this case, let's see here, in this case gives us this part right here. Okay, because that's the volume that we're adding up. Okay, so try to picture this in your mind. We're adding up the volume that we want. So we put in our pi times 4 minus x squared. I guess I misspoke earlier. The other one would give us just the area under that semicircle. But if we do this volume formula, it will give us the volume. So then we can go to Program, RAM, hit Enter. We want to go from -2 to 2. And let's just go with 10 subintervals for right now. So if we look at all that, we have 33.175 both with left and right, which of course that makes sense because if we have left-hand ones over here, they're going to be a little bit less than they should be, and over here they're going to be a little more, whereas the right-hand ones, they're going to shift, and here they're going to be a little more, and over on the right-hand side they're going to be a little less. So it makes sense for them to be equal. And then midpoint formula gives us 3.677. So let's try that again with 100. So again, we're going from -2 to 2, and we want 100. And it's going to freak out again. Okay, so if we use 100, then we get about 33.5. Well, let's just do this real quick. What's the volume of a sphere? 4/3 pi r cubed. And if you plug in your radius is, what's our radius? 2. So we have 4/3 pi times 2 cubed. And if you calculate that out, you get approximately 33.51032.164. And if you look especially at this midpoint one, you see how really close we are to getting the same thing we would with the volume formula. Now with a sphere, obviously using the volume formula is way easier than trying to go through all this. But I just want you to see, because later on we're going to get into taking some volumes of some really interesting shapes, and so we're going to need all this. But I wanted to just introduce it to you as we're looking at the RAM, because it is a very similar process. So with RAM, we're using the rectangles to find area under the curve. And we can use that same technique in volumes using cylinders. We just have to use the volume formula of a cylinder instead of the height of the rectangle. So make sure you've read section 5.1 all the way through and taken notes on that so that we can go over that in class.